Good morning, student. Myself, Dr. Govind Sharma, Assistant Professor Mathematics. Now, again with the linear algebra series, lecture series, we will discuss about the topic surface and vector. So, today we are moving forward to the linear combination and span. So, the objective of this lecture is to student understand the linear combination, linear independent and dependent vectors. Now we are moving to our lecture. Okay. So let's start. Our topic is with linear combination. What is the linear combination? What is linear combination? We are starting from linear combination. Linear combination of vectors. Combination of let Vf be a vector space. If V1, V2, Vn belongs to V, then element of V can be expressed as alpha 1 V1, alpha 2 V2 plus alpha n V. We have alpha 1, alpha 2 belongs to F. So this is called linear combination. This is called linear. Okay. Let Vf be a vector space and V is an element of V, then V can be expressed in the linear combination of other elements. This is called the linear combination where alpha 1, alpha 2, alpha n are the scalar. For example, now we take example in V3R express V is equal to 1 minus 2 5 as linear combination of the given vector V1 is equal to 1, 2, 3, V2 is equal to 2 minus 1, 1 and V3 is equal to 1. So we have to write down V in the form of linear combination of V1, V2, V3. Solution. Let V is equal to alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3. This is the linear combination. Okay. Now, V is equal to 1 minus 2 5 alpha 1 V1 is equal to, we put the value V1 here, 1 2 3. Alpha 2 is equal to 2 minus 1 1 plus alpha 3 1 1. Now we have to find out the value of, we can also write, this is column form, so we can write here 1 minus 2 5 as a vector column form, because either confusion here. Alpha 2 2 minus 1 1 plus, so 1 is equal to alpha 1 plus 2 alpha 2 plus alpha, minus 2 is equal to 2 alpha 1 minus alpha 2 plus alpha, and 5 is equal to 3 alpha 1 plus alpha 2 plus alpha. These are the three equations we get. Now from these we have to find out the value of alpha 1, alpha 2, alpha 3. Now by the solution of this, by the Kramer formula we can use, and by the simple linear equation we can use to solve it, and we get alpha 3 is equal to 6, alpha 3 is equal to 2, and alpha 1 is equal to. So the linear combination, we can be write 3v1 plus 2v2 minus 8 minus. This is our linear. This is our linear. Now we discuss about the linear span. What is the linear span? The span the span, let Vf be a vector space over field M. Then then the span S may be defined as set of all linear combination of elements of which follow the condition, follow the above definition. span as can be written as sigma lambda I vi I is equal to 1 to k belongs to n. Actually, we can define span as the set of all linear combination of v vectors. v वेक्टर्स पे जितने भी वेक्टर हैं उनका एलिमेंट्स का लीनियर कॉम्बिनेशन जो होगा उसको हम लीनियर स्पान। ओके। if S is a finite subset of P, then the span of S is set of all linear combination of the element and phi element for linear span equal to 0. But let Vf be a vector space over field, then the span F may be defined as the set of all linear combinations. Defined as the set of all linear combination of elements which follows the above definition. Span F is the set of combination, all combination of V. It's called the span. Now we will do the some theorem, important theorem on base of this. The linear span theorem statement, important theorem based on the linear span theorem. The linear span elements or subset as of a VF. VF मतलब vector space is smallest subspace of VF the containing F that is NF is equal to. In this theorem, we are asking that the linear span or subset S is the smallest subspace of VF containing S. So LS is the smallest subspace which containing S. Now we move to the proof. let U and V belongs to linear span. Then U element, which type of U element? U element is this type in linear combination. And V element is also linear combination type. We can write here where alpha I belongs to F1, F as a field, Ui it belongs to S. Similarly, alpha belongs to F and Vk belongs to F. Now, now we will show that that alpha u plus beta v belongs to F. So alpha u plus beta v is equal to alpha I ui. We put the value of ui, beta beta I, beta g, this type of value. Now the multiplication and summation. Now this is constant, multiply with constant, we can combine this alpha alpha I vi plus beta beta j vj. This is also linear combination. We can put alpha alpha I as alpha and it become, so we show that alpha u plus beta v can be expressed as linear combination of okay. That means alpha u plus beta v now belongs to F and uv belongs to F. Implies alpha u plus beta v is also. Thus, that is the space of Vf and each element of U is element of Ls because U is equal to 1 dot U belongs to the Ls is the subspace of S. Now each element of S, V is element of Ls. So V U can be write as 1 dot U and U is the element of linear combination of S. Now we will show for all for all U belongs to S, U belongs to L. Implies S is a subset of S. Now if now if W is subspace of VF. Now if W is the subspace of VF, then now if W is subspace of VF. Now we will show that Ls is the smallest subspace containing S and W and W and W is closed vector multiplication and scalar and color product. Scalar product. Now if W is the surface of VF and W is the subset of S and W is closed for VF multiplication and scalar product. So each element so each element so each element each element of LS is also element of W. That LS W plus LS is equal to this, and so ls is ls is smallest containing theorem if f and t are subspaces of Vf, then s plus t is a subspace of Vf, and s plus t that is linear span s union t is equal to. Here we have to show that S and T are subspace of vector space V, and S and plus T is a subspace of V. We have to show that S plus T is also a subspace of. Okay. So here we are again prove that alpha u plus beta v is the part of S plus T. Now for a subspace we will show proof. We know that for a subspace we have to show that alpha u plus beta v is equal to belongs to S plus. Let let u1 u2 belongs to S, and v1 v2 are belongs to T. Okay. So by the definition of S plus T, which type of element by, so by definition of S plus T, u1 u1 plus v1 belongs to S plus T, and u2 plus v2 belongs to S. Now we have to show that S plus T is a subspace. So we take alpha beta belongs to S. Why? It is the subspace if alpha u plus beta v belongs to S. S plus T. We put alpha first element u1 plus v1 plus beta u2 plus v. Alpha u1 plus alpha v1 plus beta u2 plus beta. Now here we can write in the form of alpha u1 alpha u1 plus beta u2 and alpha v1 plus beta. This belongs to because S and T are also subspace because S and T are also subspace. We have already proved that linear span is a smaller subspace which containing S. So S and T are also subspace. So if alpha u1 u2 belongs to S and alpha belongs to S, so and beta belongs to S. So that implies we can say alpha u1 plus beta u2 belongs to for irreducible. Similarly, we can say v1 v2 belongs to S, alpha beta belongs to S, so alpha v1 plus beta v2 belongs to here t. If t is a subspace, this is equation 2, this is equation. So by 1 to 4 we understand that alpha u plus beta v belongs to S. By 1 and 2 we can put the value by 1, 2, 3 we can conclude that we need here we see in equation this is from subspace S and this is from subspace 2. So we can make S. Now again I explain this theorem. We given that S and T are two surfaces of VA. Then we have to show that S plus T is also a surface. For this we know for a condition of surface alpha u plus beta v is equal to belongs to W. If W is a surface. So we take two elements v1 u2 from S and v1 v2 from T. Then by the definition of S plus T, the element one first element taken from here and second element taken from here. The sum of this is u1 plus v1 belongs to S. Similarly, u2 plus v2 belongs. Now we take alpha beta belongs to. So alpha u plus beta v belongs to S plus T. Means alpha u plus beta u2 plus v2. Now we open this to become alpha u1 plus beta v2. Alpha v1 plus beta v2. The sum of this becomes S plus T. This S plus T. How this is from S alpha u1. How we can say that this is from S? I explain here. I explain here that if S and T both are the surface, so u1 u2 belong to S, alpha u1 plus beta u2 belongs to. Similarly, T is a surface, so alpha v1 plus beta v2 also belongs to. So these are the surface, T is a surface, S is a surface, so S plus T is also a surface. So this is very important theorem. The result is very important that the sum of it can be theorem can be written as let prove that it can be written also like this. So that the sum of two vector space, two vector subspace is also now student move for the quiz question. Which is a vector space? Set of polynomial, set of natural number, filled over the subfield and not. I already told you that multi answers are can be correct. Multi option are be correct. So the first is the set of polynomial is a vector space. We already explained did this exercise that the set of polynomial follow all the condition of vector space. So set of polynomial is a vector space and set of natural number. Second, first is right. Set of natural number is wrong because set of natural number is not a Billion group. And is third is filled over the subfield. Filled over the field definitely uh, over a subfield is also a vector. So option A and option C both are the right option and B and D are the wrong. What is true? Union of subspace again a subspace. This is wrong. Intersection of subspace again a subspace. This is right because the intersection of two subspace like S and T are two subspace. Then the union of subspace is not the subspace but the addition of two disjoint surfaces are always a surface. We already proved it today. The intersection of surface will be a surface. So B is the right. C set of matrix with real entries are linear surface. This is also right. Linear number it may be real number. Real entries is 0, 1. The identity is covered. Inverse element also covered, multiple inverse is also covered. So this is a linear space or vector space. Which is the true for subspace? There exists always zero vector y NWYBBA which is a true for success. There exists always a zero vector. Right, this is right because the image of zero vector is always zero. So there exists zero vector. Zero element always there. Vy in W is right. V is a constant and y is the product with vector. A plus y is W is right. So R all is right. So three options. So D is the right option. All are true. A vector V is the direct sum of U and W if they are disjoint vectors. These are the linear intersection of U and V. W is 0. So A and C are the right option. A vector V is the direct sum of V and W, then there are joint vector space wrong. There is a disjoint vector space. So student, I hope today lecture you enjoyed and clear your concept about the linear combination. Your quiz will be in next lecture. So thank you very much.